All right, thank you for the introduction. We're approaching the end of the day. We've heard this quite often today, but I believe we cannot stress this enough. First of all, thank the organizers for assembling this beautiful workshop. We have some great days ahead, and I'm very much looking forward to them. Along these lines, I would also like to acknowledge collaborators, most notably the three you can see on top, all of them working in Berlin, 2 of them being present here today. And last but not least, I'm in the fortunate position to thank my predecessors on the stage today because they've already introduced most of the concepts I'll need in my presentation, so that is absolutely excellent for me. What I'm planning to talk about is also along the lines of fluctuation-induced phenomena, atoms interacting with thermal fields with surfaces. Basic setup is, well, we might have a bunch of atoms, somewhat trapped close to a surface. I'm not caring too much about the trap, but in most experiments there will be one present. What I care more about today is fluctuations of the vacuum, the material, thermal as well as quantum fluctuations that induce interactions between the atoms and the surface. And I'll do it even simpler and say, well, we don't have a bunch of atoms, we don't have a realistic trap. No, we only have one atom, and model that also by a dipole. Of course, we have already heard today higher order moments are important and should and need to be included, but this is some future work of more intelligent people. Well, one general motivation on why would do that, apart from the academic reasons of that these forces are just interesting. Well, atoms, when separated and studied, don't really, or let me start differently. Atoms don't like to be separated and studied. They don't want to be separated. They want to be among others. They don't like that, which makes it hard to achieve that in experiments. Therefore, they're very sensible to any disturbances in those experiments. But once you got there, this sensibility makes them marvelous sensors. You can use them to sense forces, line shifts, dissipation rates, stuff like that, gravity, as we've heard, so on and so forth. And many of those being used for computation also, many of those sensors work on lab scale, but it would be extremely convenient to integrate them, to miniaturize them, just put them in your pocket, carry them away. And in very, very simple arguments, that means the environment comes closer, geometry becomes important, materials becomes important. We have heard this often today. And that's what I want to basically talk about in my talk today. It's atom field interactions at finer temperatures, but there does not need to be only one temperature. There can be 2 or multiple, and that's what I call non-equilibrium, thermal non-equilibrium. They are, just as a teaser, of course, different kinds of non-equilibrium. A bunch of these atoms could also be in motion with respect to a surface. That then effects called friction occur. And just as a teaser, in case anyone's interested in that, we have just a recent publication on the connection between thermal radiation and frictional forces. And if you don't care for reading too much, we also developed a nice numerical tool where you can play around with those forces, insert some materials, and get some numbers out of it. This just as a teaser. In the following, I'll completely concentrate on thermal non-equilibrium. And as we've learned today, this interaction of atoms with thermal field looks back to almost 2 orders of magnitude in history now. So you'll find a huge number of publications on the topic. You'll find very different nomenclatures. You will find different effects. I, without any bias, just took 4 examples I found interesting that you may come across if you Google for these types of interactions. Quite often, especially in clock interactions or frequency interactions, the frequency shift of atoms due to blackbody thermal radiation is of interest because you need a very precise understanding of what the reference frequency is in order to calibrate that to your instrument. People then also add what they call dynamical corrections, which is basically properties of atoms, that they are being added. But there are also other more recent experiments appearing where in vapor cells, the reference frequency of these atoms is being probed, and in 2 geometrically different setups, they already can resolve geometry dependencies of thermal radiation in the line shifts. Then just to drop more names, there can also be forces from non-isotropic thermal radiation. You see, incrementally, I'm adding more and more geometry to the story and more non-equilibrium, which have been by some members of the audience, measured by some members of the audience some years ago. And what we've heard a lot about today is, well, whatever type of Casimir-Polder interaction you can have in thermal equilibrium and non-equilibrium. And for the remaining minutes, my promise is more or less to say, well, if you have come across one of these experiments or names or topics, I'll try to make the connection to the other, just motivating that they all are lying on the same fundamental footing. And then I'll do just present some examples how geometry enters the game, how materials can modify the interaction, and I'll focus on the thermal non-equilibrium part here. Just motivate some scaling laws. But let's start with the first situation, just what is the theoretical foundation of all of these experiments? And repeat some fundamentals. Well, any type of thermal radiation, usually, at least we have seen in the experiments today, originates from a warm body at some temperature. In the simplest case, the dimensions of that body, this is just a sketch of the idea, is much larger than any thermal wavelength, so the geometry is not being resolved by the interaction. And then we become what we all know very well from university. Don't mind the log-lin scale, a little weird, but you have standard blackbody radiation in a Planckian spectrum. This does not need always to be the case. Well, if you can indeed, put this quotation marks, kind of, quote-unquote, resolve the geometry, well, you don't have blackbody radiation anymore. You have something that's non-isotropic thermal radiation, and we have heard a lot about that this morning. And last but not least, I said there will also be non-equilibrium. Not every temperature has to be the same. That will again change the spectrum of the field, which will interact with the atoms, your sensors that you're interested in. And in very simple terms, it will just say whatever energy you're referring to, which could be a transition line, is now is changing and depending on position, different temperatures, and especially the geometry and the materials of the environment. And we have heard already something about nomenclature today. I will now kind of pledge allegiance with the intravia story of that and say there are atoms involved in macroscopic bodies. So for me, this is already Casimir-Polder. Usually, Casimir-Polder is referred to an equilibrium situation. I'll extend it and say same theoretical footing. So this is just, even in non-equilibrium, a common Casimir-Polder force, but with this little extra attention of non-equilibrium. Very little importance of that, just a side note which I added in the break. Now, I said we want to talk about geometry. So in the vicinity of bodies, it all comes down to field correlations. And I'm very happy that we heard a lot about that this morning. So what I'm trying to sketch now is the theoretical overview of how you would approach that system systematically and introduce a number of approximations step by step, where then you could whatever name you would like, add whatever name you would like for the effect. Incrementally, we will ignore more and more geometry, more and more non-equilibrium, so come from Casimir-Polder all the way down to simple standard blackbody radiation. It all starts with a Hamiltonian. We are theorists, and there's a little side remark here. You do not want to thermally excite the atom, so that is kind of a limitation on the temperatures we are interested in. What then we have learned this morning we should do is do fluctuation electrodynamics, which is a very intricate field, but for the purposes of the story, a little bit too much to explain now, I think. So I think it would be simpler to say, well, we simply do perturbation theory. And please believe me for the moment, with a certain number of approximations, you'll end up with a very similar result. One difference, though, that might be interesting, usually since we do non-equilibrium, it's more safe to speak in terms of forces, not energies, due to their definition, but we'll sweep that under the carpet now. Well, standard perturbation theory, what do we get? Bettina nicely introduced that this energy shift, now with, again, position, different temperatures, is a broadband phenomenon, and it will depend on atoms, atomic properties, and field properties. And a very simple approximation I want to make is, I don't care for any different temperatures for non-equilibrium. I don't care for the position of the atom. I simply erase them, and what I end up with is just by two-line derivation, blackbody shift and dynamic corrections, as they're being often used in atomic clocks or frequency references, as I motivated earlier, where the full elegance and power actually lies in calculating the atomic properties in front of those expansion coefficients. That's where all the detail and the work goes in from my understanding. But of course, per definition, less the geometry of the environment. Well, if we don't do that approximation, geometry enters. It all comes down to the field correlation. And unfortunately, I wanted to save you the fluctuation in electrodynamics, but it here comes kind of via the back door, back into the game again. Well, never mind. This was the broad overview, which more or less motivates, started by this Hamiltonian to the top left, that at any of these points you can kind of insert the effects you find in the literature and kind of combine them and set them in the appropriate place. First thing. Now let's get more concrete and talk about the explicit laws, scaling laws, and maybe put some numbers on those forces. And luckily, we have already seen a lot about that today. I'll talk about an experiment of Obrecht et al. It's quite an old experiment. I'm not going to bother you with too many formulas, just say that, well, what they did was trap a BC close to a surface which was heated, and then they measured the Casimir-Polder interaction in thermal non-equilibrium, which, as I tried to motivate, covers most of the effects one might be interested in. And what they did was, well, you see two plots. One is a function of distance, the other one is a function of temperature, and it's a trapping frequency, a change in trapping frequency, just say a measure of the strength of the force. The only thing I want you to take from that is the higher the temperature with respect to the environment temperature, the stronger the force for larger distances. So if you want measurable forces at large distances, thermal effects are important. And the reason for that, we have seen often today, is just different scaling laws in terms of distance and temperature. And in fact, there's also another situation. In equilibrium, we get t to the power of over the power of distance to 3, and in the non-equilibrium contribution for different temperatures then scales again differently. Not a blank spectrum, that's maybe interesting, but another change in the distance law, making it a dominant contribution in certain large distance regimes. Well, is it always like this? I'm trying to motivate no. Let's try another geometry. Well, I'm a theorist, the only one I can think of different from a plate is a sphere. So this is very different from a plate for me. Same situation. Well, okay. Unfortunately, we can't now look into the literature and just copy the result. We have to calculate it on our own. What we need to do is to find an expression for the field. Important here is, due to this, we'll have a dispersion relation relating frequency to wave vector dependencies. Meaning, whatever geometry you have, that will change the wave vector distribution, and that will change your frequency dependence. Well, we have the thermal occupation of the field, so most likely what I call small frequencies will be important of whatever field distribution you find. And then, well, find the expressions, calculate your integral, and the scaling laws come from frequency and geometry, where the frequency usually translates into temperature, geometry translates into distance scaling laws. However, they are connected. Well, more concrete, we learned this morning, the field is basically the expression of the correlation function of the electric field operator in this approximation. And for that, luckily, we know the solution. We just need to ask our friend Maxwell, calculate the green tensor. Once we have that, life is simple. Let's look that one up for a sphere. There's a marvelous book of Tai, the Adic Green's function in electromagnetic theory. My original take on that was it's horribly tedious to look up the actual results. However, so I won't talk about this in this talk. However, I'm obviously ignorant. Bettina corrected me here last week. It's an acquired taste. Indeed, that book contains a lot of answers to many questions you might have, and plenty more answers to questions you probably will never hope to have. Anyway, it's a tedious task to copy the green tensor here, so let's do a simplification. Let's rethink what we're actually interested in. I said earlier, the geometry, if you want a measurable force at large distances, usually you're interested in the thermal components of the force. Well, we want to go to large distances, so we don't need a full expression of the green tensor. And at large distances, both the atom and the sphere more or less look like a dipole. And two dipoles interacting with each other over the vacuum electromagnetic field, you can simply use, the vacuum green tensor, which for those who have worked with those green tensors, you can simply copy from a book. That's a one-line expression. And in this way, you transform your tie to just the back of the envelope calculation to get a simple estimate and a feel on that. What happens is, well, don't follow that, it's just for the purpose of the story. The spectral density of modes, spectral mode density, in this non-equilibrium situation, using a conductor described by the Drude model, for those large distances of the two dipoles interacting with each other, Drude model for the sphere, by the way, scales as frequency to the power of 4. Performing the integrals, you get temperature difference to the power of 6 divided to the combined distance, which is radius plus distance from the surface, to the power of 2. Again, another scaling law. Again, not the Planck law. And depending on the parameters, depending on the materials, depending on the material models especially, and depending on the particular situation and geometry, there will be many more different scaling laws. There's no guarantee to ever have t to the power of 4 dependency of these forces. You'll have to do the math in each individual case, which is more or less the second take-home message here. There can be a number of scaling laws. Well, that is my summary now. I said what I wanted to try to convey to you today is, one, many of the effects that are being used in experiment connected to thermal radiation can be described more or less on the same theoretical footing. Number two, it's, at least from my experience, not trivial to guess what dependence and scaling laws you will achieve in your particular situation. Changing small things can change power law and temperature, power law and distance. You'll achieve various scaling laws. And with that, I'm looking forward to questions.